In this video, we begin chapter 7, covering section 7.1, Eigenvalues and Eigenvectors. So in the series of videos for section 7.1, we have the following learning objectives. So again, these will be spread out over 3 videos. So we are going to prove properties of eigenvalues and eigenvectors. We are going to verify eigenvalues and the corresponding eigenvectors. We are going to find eigenvalues and the corresponding eigenspaces. We are going to use the characteristic equation to find eigenvalues and eigenvectors. And we are going to use software to find eigenvalues and eigenvectors. I'm going to show you how to calculate in SIMPy, but you are also welcome to use the TI graphing calculator. So I do include some screenshots showing you how to do these calculations in the TI graphing calculator. This section presents one of the most important problems in linear algebra, what's known as the eigenvalue problem. Its central question is, when A is an n by n matrix, do non-zero vectors x in Rn exist such that Ax is a scalar multiple of x? So some matrix A multiplied by vector x, is that a scalar multiple of vector x? So the scalar is denoted by the Greek letter lambda that we see right here. And when you draw it, if you just want to use L, that's fine. Or I make, the short leg and then the longer leg first to get my lambda symbol there when I draw it by hand. And so that lambda is called an eigenvalue of the matrix A. And the non-zero vector x is called an eigenvector of A corresponding to lambda. So make sure you note that x has to be non-zero because none of our calculations really make sense. They're all trivial if x is 0 vector. So the origins of the term eigenvalue and eigenvector are from this German word Eigenwert, meaning proper value, or sometimes people say it means a particular value. So here's our overall relationship. Matrix A times eigenvector x equals some value lambda that we call the eigenvalue, a constant, multiplied by eigenvector x. So eigenvalues and eigenvectors have many important applications, many of which are discussed throughout this chapter. So for now, you will consider geometric interpretation of the problem just in 2 dimensions in R2. So if lambda is an eigenvalue of the matrix x, the matrix A, and if x is the eigenvector of A corresponding to lambda, then multiplication of x by the matrix A produces a vector lambda x. Lambda x is going to be parallel to x, and we see on the left, if lambda is positive, it just extends vector x in R2. And on the right diagram, we see if lambda is negative, it extends vector x in the negative direction. So an important note is that the eigenvector cannot be 0. So saying matrix A times a 0 vector equals lambda times a 0 vector is true for all real values of lambda. So an eigenvector being the 0 vector is really meaningless. So eigenvalues of lambdas can be 0, but we don't ever do 0 vectors as eigenvectors. So here's our definition of the eigenvalue and the eigenvector. So A is always going to be a square matrix, n by n. The scalar lambda is what's known as the eigenvalue of A when there's a non-zero vector x such that this relationship holds true. Matrix A times vector x equals this non-zero value, or it could be 0 value lambda multiplied by the non-zero vector x. So the vector x is what's known as the eigenvector of A corresponding to this value of lambda. So let's take a look at an example. So we're going to verify here that lambda I, where this is lambda sub I, because you can have lambda 1, lambda 2, etc. for your eigenvalues. So we're going to verify that lambda 1 and 2 here in this example are eigenvalues of A, and that x1 and x2, the xi's, are the corresponding eigenvectors here. So A is a 2 by 2 matrix. It's got 2 and negative 2 on the diagonals and zeros everywhere else. And so we're going to check to see lambda equals 2 and lambda equals negative 2 are the corresponding eigenvalues for these eigenvectors 1, 0, and 0, 1. So here's our solution. We've got matrix A multiplied by x1 here. That's the 1, 0. And we see, oh yeah, well, that's just going to be 2, 0, but we can factor out the 2 and multiply it by 1, 0. And so that's our lambda 1 x1. And then similarly, we can do matrix A times vector x2 and we get 0, -2, well, that's just like a -2 multiplied by this vector x2, so that's lambda 2 x2. So we verified that these values 2 and -2 are eigenvalues of matrix A, and then the corresponding vectors are our familiar standard basis vectors in 2 dimensions, 1, 0, and 0, 1. So let's look at another example in 3 by 3 matrix situation. So we're gonna verify that lambda 1, lambda 2, and lambda 3 here are eigenvalues of A, and that x1, x2, and x3 are the corresponding eigenvectors. So our first calculation here is we do A, matrix A times x1, and then we get here this vector 2, 0, 0, and we see, oh yeah, we can factor the 2 out, and so that gives us lambda 1 multiplied by vector x1. Then we do in the next calculation, same matrix A now multiplied by x2, and we see that gives us the negative version of x2. So we're able to say that -1 times vector x2 is lambda 2 x2. And then for our third calculation down here, we've got matrix A times vector x3, and so we get 15, 3, and 6, and you can see right away you can factor 3 out. And so that's 3 as our eigenvalue multiplied by vector x3. So eigenvectors of lambda actually form a subspace. So we're going to see that here in theorem 7.1. So if A is an n by n matrix with an eigenvalue of lambda, then the set of all eigenvectors of lambda together with the 0 vector, because we need that 0 vector to be a subspace, form a subspace. So we say in mathematical set notation, this is all values of x such that x is an eigenvector of lambda joined with or unioned with the 0 vector. And so we say those are all the x's such that ax equals lambda x, and those form a subspace. So here's our proof. So we know x such that ax equals lambda x is not empty because it contains the 0 vector. We know that ax equals lambda x is closed under scalar multiplication because for any vector x in this set where all the ax's equal lambda x, and for any scalar c, we know a multiplied by c of x, you can factor that scalar c out, so that's c multiplied by a of x, a times x, sorry, and then c multiplied by lambda x, or lambda multiplied by cx, because we can multiply these scalars in any order here in the real values. And then our third thing to show is closed addition. So we know that the x's where ax equals lambda x is closed under addition, because for any vectors x1 and x2, where ax equals lambda x, we can write a multiplied by x1 plus x2 by distributive properties of matrix multiplication. We know that's a x1 plus ax2, and then we know ax1 is just lambda x1 and ax2 is just lambda x2, and we can factor the lambda out to get lambda multiplied by x1 plus x2 vectors. So we have shown that the eigenvectors form a subspace. In the next video, we're going to see how to find eigenvalues both by hand and by using SIMPy technology.